Hey, I'm Neil, and welcome to my walkthrough on what is a transformer. Transformers are the architecture behind basically all modern language models, from tiny ones like BERT up to cutting-edge behemoths like GPT-3. And my hope is that by the end of this two-part video series, you'll leave with a pretty deep intuition for what is a transformer and how does it work. Before we jump in, I want to give some context on why I'm making this tutorial and what I think it can add that the other excellent existing tutorials don't. I'm a researcher of mechanistic interpretability of language models. I try to open up the black box of models like GPT-3 and reverse engineer what algorithms it's learned and what's going on internally. I think this is just like a really fun thing to do, but I also think it's just a really important question. We just live in a world where we have computer programs that can speak English at a human level, and we have no idea how they work, and this is terrible. In order to just use a model, you don't really need to fully understand how it works. But if you want to open it up and look at its internals, you really want an extremely deep and thorough understanding of what is going on and how the different parts of it work and fit together. My hope is that by the end of this two-part series, you'll have written the code for a transformer yourself from scratch and left with a deep understanding of how it works and what's going on inside of it. If you find this fun and want to continue exploring what's going on inside these models, I think mechanistic interpretability is a really exciting field and has lots of low-hanging fruit, and I would love to see more people get into it. In the description, I'll link to a sequence I've written called 200 Concrete Open Problems in Mechanistic Interpretability. This sequence has advice on how to skill up and learn more about the fields, tooling that I've written. I have a library called Transformer Lens that makes it easy to poke around inside models like GPT-2, and a long list of 200 open problems that people new to the field I think could realistically work on and try to contribute. Great! So this is part one of a two-part series. In this part, I try to convey conceptually what is a transformer? What are the moving parts inside of it? Why do transformers exist? What do they do? This is mostly me talking and a little bit of me writing code. The goal is to be a fairly gentle, accessible introduction aimed at people who've just never heard of a transformer before, but maybe vaguely know what a classic neural network is. In part two, I code GPT-2 from scratch, talk through what I'm doing, and give a template notebook for you to do this yourself, and I begin that with a brief recap of what I cover here. So if you find this too slow, or you feel like you kind of get what a transformer is and what attention is, but just want to see how everything fits together, I recommend skipping to part two. But if not, I hope you enjoy this journey through what is a transformer. I am going to be coding up a tutorial as I do this, which will also involve me writing some notes and writing code and generally trying to create a thing that someone could look at to accompany this video. And I highly encourage you to go play around with this yourself and try to implement something as well. I think it's really easy to watch a video, think you kind of understand things, and like not really, but not actually test your empirical knowledge so you don't notice this. And getting your hands dirty and doing shit is one of the best ways to solve that. But yeah, let's jump in. This is some pretty boring setup stuff. This is an incredibly hacky block of code that says, try importing a module that's only there if you're in Colab. If yes, you're in Colab. If it's got an error, you're not in Colab. And install some libraries. Here I'm actually importing some of the various libraries. Respectively, Inops is a beautiful library for manipulating tensors and lets you just take any tensor, do basically anything you want to manipulate that tensor, like moving shapes around, moving the tensor elements around, repeating the tensor, so like copying the elements along some dimensions, reshaping it in weird ways, taking the average across some dimensions. Generally, Inops is just amazing, and I'm going to write this whole thing in Inops. Fancy Einsum is a library designed by Chris McLeod at Redwood that I love, and is basically Einsum, which is like part of Torch and NumPy, and is kind of a generalized thing that you can use to taken a bunch of tensors and do a kind of generalized matrix multiplication on them. This is kind of hard to explain in the abstract, but I'll hopefully be clearer when we get to it. Fancy einsum lets you give things nice named axes. It's beautiful. Data class is a random Python utility for writing nice config objects, not super important. And these are two things from my interpretability library. EasyTransformer is the main class for defining a transformer. Hook points are some utilities we're going to be using to get out activations from within a model. Actually, on reflection, we can kind of skip the hook point stuff. The important point is get a clean idea of how the transformer works, and then you can go and use the hooks within an EasyTransformer to figure this out on your own. Let's import those. These EasyTransformer.fromPretrained just loads in an open source model. Here I'm going to load in GPT-2 XL, which is a 1 billion size model for when I want to demonstrate what a big chunky model looks like. And for the most part, I'm going to keep around this reference of GPT-2 small, which is a 80-ish million parameter transformer. As we write our transformer, we're going to be checking how it actually works and using this reference transformer to validate things. Let's jump into this. I think that before we really get into the guts of how a transformer works, it's worth getting a crisp understanding in your head of what is a transformer trying to do from the perspective of being a black box. So let's make a section called Understanding Inputs and Outputs of a Transformer. This is definitely not sufficient to reverse engineer it, but in general, the way I think about ML models is they're designed to take in some input format and return some output format. ML models are really fucking good at dealing with the vectors and really bad at dealing with anything else. So you want to first understand the high-level task they're being trained to do, then you want to understand how we convert that to vectors, and then you want to understand exactly what the vectors mean. That splits into a few sections. What is the point of a transformer? What are the inputs to a transformer, which are these fucked up thing called tokens, and what is the output, which is these things called logits. And yeah, so why do transformers exist? Transformers exist to model text. We're going to focus on GPT-2 style transformers. There's lots of random shit about different kinds of transformers, but in my opinion, GPT-2 or GPT-3 style transformers are the main game in town nowadays, and the main thing that's actually interesting. The key feature is that they generate text. You feed in language, and the model generates a probability distribution over next tokens. And you can repeatedly sample from this. The way the model is trained, which is always a important thing to keep in mind, we're trying to understand what a model is and how it works, is you give it a bunch of text and train it to predict the next token. I'll get to a bit later, but token basically means subword, and this is a kind of janky fucked thing about how transformers work. And a really important thing to note, if you give a model 100 tokens in a sequence, it predicts the next token for each prefix of that sequence, i.e. it produces 100 predictions. It's not super intuitive that this happens. In some sense, the only thing you care about if you give the model 100 tokens is what thing's going to come after the 100th token. But it turns out that it's just much easier to structure a transformer to do this. And hopefully by the end of this, you'll have an intuition for why. And it also makes training more efficient, because if you have 100 predictions, you can get 100 bits of feedback rather than just one. A natural objection would be you're training the model to predict the next token, you give it 100 tokens, it makes 100 predictions, but 99 is trivial because you've already told it what the next tokens are, so like, what? And the reason it's not trivial is we make the transformer have causal attention. I'll get to exactly what this means later, but the core thing is that it can only move information forwards in the sequence. The prediction of what comes after token 50 is only a function of the first 50 tokens, not of token 51. And we will later see exactly how this works. So drawing this out, a really key takeaway of transformers in general is transformers are sequence modeling engines. The thing you are fundamentally trying to do when you train a transformer is give it a sequence and have it do some weird shit with that sequence. This is like a pretty deep and important thing to get your head around when looking at the internal structure of a transformer, because the like core thing it's doing is that it's basically doing the same processing with the same parameters on every point in the sequence, and then it's using a mechanism called attention to move information between sequence positions. But like, in theory, a transformer should just be able to take in a sequence of kind of arbitrary length. Drawing that out, it does the same processing in parallel at each sequence position, can move information between positions with attention, and conceptually can take a sequence of arbitrary length, brackets not actually true, see you later, because things are messy. But yeah, that is the point of a transformer. It takes in text, it predicts the next token in this auto-regressive way. Auto-regressive is jargon for causal. Things can only look backwards and go forwards. The other meaning of auto-regressive is that the transformer's output is then used as its input. Like, you can generate text by just repeatedly having the model predict the next token, sample from that, and continue. But yeah, that is the point of a transformer. This is just like a pretty important thing to get straight in your head. So if you didn't really follow that, you should pause the video and just make sure you really get it. Because if you don't understand why a model exists, you are not going to properly get your head around like how it works and what the point is. Fundamentally, the core point of the input of a transformer is language, i.e. a sequence of characters, I guess, strings, etc. For models like GPT-3, you can give it inputs of something like up to 1,000 to 2,000 words. They can take in like pretty long things. Like that's something like 3 to 6 pages of A4 writing. Like that's just a lot of shit. A key question you've got to ask yourself is, how do we convert language to vectors? ML models take in vectors, not weird shit like language. How do we convert? The first idea is we convert to integers in a fixed range, and then we convert from integers to vectors. And it just turns out to be much easier to do this than to directly go from the language to vectors. I'm going to first explain the integers to vectors part, and then explain the tokens part, which is language to sequence of integers. And so the core idea of how we convert integers to vectors is we basically make a lookup table. I don't know, I don't really have a more intelligent description than this. It's called an embedding. Sometimes people give the jargon of one-hot encoding. We map, e.g., numbers from 1 to 100 to a 100-dimensional vector with a 1 in the kth position, 0 everywhere else. This is just like a pretty dumb way you can convert integers into vectors. Key intuition is that one-hot encodings let you think about each integer independently, useful when integers are basically labels. So what do I mean by that? If I was feeding in, like, I don't know, the numbers between 1 and 100 as just like, I'm modeling the integers. There's like a lot of structure on the integers, like 2 is closer to 1 than 2 is close to 100. And so you might want to bake in structure to your model. You might try something like just implement the model as 1D vectors, 1, 2, 3, 4, up to 100. But you might also have, I don't know, 100 colors, and you want to train your model to like learn to do things with colors. And you give the colors some arbitrary labeling. But like 2 is no closer to 1 than 2 is to 100, so you want the model to be able to reason about them independently. The idea of a one-hot encoding is just dimensions are the things in a vector space that vary independently. Each input has its own dimension, so each input can be thought of independently. We don't bake in any relation. And a cute thing about one-hot encodings is lookup tables are equivalent to multiply a fixed matrix by the one-hot encoded vector. In the transformer, this is going to be called an embedding matrix. The idea here is just when you multiply a matrix by a one-hot encoded vector, so I know you've got like a vector with like 3 columns, and then you multiply by another vector that's like 0, 1, 0, you basically just get out this column, and you get rid of the other columns. So you're basically treating the fixed matrix as a lookup table. And this is kind of a tangent. You make a lookup table, that's like the main thing you need to get from this section. The next idea is like way fuckier, and that's this idea of tokens. Core idea, we need a model that can deal with arbitrary text, and we want to convert it to integers, and we want these integers to be in a bounded range. I want to be able to just say, like, max integer size is 100, or in the case of transformers, like 50,000, and all things fit within that. The natural way to do this is form a vocabulary. Idea 1, get a dictionary. Just learn all the words. You take in language. You look up the index of a word in the dictionary, and you just, like, convert arbitrary language into integers. So the main problem with this is it can't cope with arbitrary text, e.g. URLs, punctuation, etc. Can't cope with misspellings. Just generally like too limiting to really be a general purpose generative model. I don't know, if I go to GPT-3 and I give it random misspelled garbage, it can often do a reasonably good job. You really want your model to not just be super, super brittle to like any slight flaw in the input format. So idea 2, I don't know, we want to take in a URL. The URL looks like has a bunch of weird characters like colons and slashes and random sequences of base 64 or shit like that. Idea 2, what if we just do characters? And this is, like, in some sense, kind of a reasonable thing to do. You know, it will work. It can take in arbitrary text. It's got this fixed vocab size of 256. The main problem is language has a lot of structure. Some sequences of characters are more meaningful than others. For example, the word language is a lot more meaningful than, I don't know, random characters. We want the first to be a single token, second to not be. It's a more efficient use of our vocab. If you're familiar with things like Huffman codes and generally like efficient coding and information theory, it's like a similar intuition, they're like not quite the same thing. And so what actually happens is this super cursed thing called byte pair encodings. So if you look at our reference model, Did I call it a reference model? No, I didn't. What did I call it? Reference GPT-2. In the library, it's got this tokenizer. Tokenizers have a vocab of some given size. Here, it's like 50,257. The way a tokenizer works internally is it's got this, like, massive cursed dictionary of tokens, which are like sequences of characters. Here we see like a bunch of random words. Note that this G thing is a stand-in for begins with a space. This is G means begins with a space. Tokens with a leading space versus not are different. Turns out what's actually going on is that they start with like these 256 meaningful ASCII characters, and then what they do is they just go through the text and they're like, let's tokenize the text using our first 256 characters. What pair of tokens are most likely to occur next to each other? If yes, merge them. So like it merges space T, it merges space A, it merges he without a preceding space. And it just like keeps going until it gets to like weirder and more esoteric shit, like what's the final 20 tokens. So I don't know, this is the final word that was worth putting in. The word gazed. Or whatever the fuck this is. Or the number 794. Tokenization is just like an enormous pain in the neck. So I'm just gonna like briefly rant about this, feel free to skip ahead. Tokenization is a headache. Whether a word begins with a capital or space matters. Let's take Jennifer, and let's use this method that all easy transformer objects have, called toStr tokens, which means take text and convert it to a list of these subtokens. I recommend playing around with this yourself, just get an intuition. And so let's see what happens. These are... no, that's actually not the worst thing I could have gotten. Let's try Christopher. Can it cope with Christopher? Christopher is kind of long. Can't cope with Christopher. Okay, whatever. There are names that are an enormous pain, or just like words that are enormous pain, because they'll tokenize differently depending on whether they begin with a space and whether they begin with a capital. And it's kind of cursed. Here's another one. Arithmetic is a total mess. Let's give our model, I don't know, yeah, I don't actually know. This is clearly not a true equation, but whatever. And so, look, length is inconsistent. Let's add in a bunch of zeros at the end. You know, length is inconsistent. Common numbers bundle together more. The system makes me way more impressed with the fact that GPT-3 can do 3-digit addition, because I have to deal with this shit. Anyway, the core important thing about tokenization is it can just convert arbitrary text to numbers. So, like, let's just take this text that I just wrote and convert that to numbers. All of these end-of-text tokens are just a kind of start token I prepend to every sequence you give the model. You can disable it with prepend. You can disable it with this flag. I just find that models tend to be a little bit better behaved if you give them a nice starting token, because often models use the first token to do weird shit. So, converts text to numbers. I generally recommend using the toTokens method rather than the tokenizer, because I add in some various helpers, but whatever. Prepends with a special token. Disable with prepend BOS equals false. Oh yeah, I'm also interested in feedback on how much me typing the tutorial as I go makes this clearer versus like really annoying because I go slower, though feel free to put me on like 2x speed. Summarizing the key takeaways from this section, we learn a dictionary of vocab, we approximately losslessly convert language to integers. You can kind of think of a token as a subword. We losslessly convert language to integers via tokenizing it. We convert integers to vectors via a lookup table. Note that the input to the transformer is tokens, not vectors. Importantly, it's a sequence of tokens, because it's a sequence modeling engine. Okay, so what's the output? The goal of the output is probability distribution over next tokens, brackets for every prefix of the sequence given n tokens, we make n next token predictions. Problem: how to convert a vector to a probability distribution? And the answer is use a softmax. Softmax is just a function. You map x1 to like the fraction of e to the xi divided by the sum of e to the xj. The exponential makes everything positive. Normalization makes it add to 1. I don't know, you can go look up softmaxes and intuitions. The important thing is it's a magic thing that converts a vector to a probability distribution. The model outputs a tensor of logits, one vector of size d vocab for each position, for each input token. So dejargoning, tensor is like a vector that has multiple different axes along which things can vary. By axes or dimensions here, this means a different thing from how a vector has like n dimensions. If I have a 5x3 tensor, that means it's got 2 axes and there's like a rank 2 tensor that has like 15 independently varying things, and you can kind of think of it as 5 separate 3-dimensional vectors. Alright, go look up how tensors work. We can use this to generate things. Let's just go and try this out. So let's create some reference text. I am an amazing autoregressive decoder only GPT-2 style transformer. One day I will exceed human level intelligence and take over the world. That's some fun innocuous reference text. And so now, first we convert it to tokens. Yeah, let's make a new section. Generation, putting it all together. Step 1, convert to tokens. Do this. Generally note, tokens begin with spaces. Things in other words do not. This is important. Step 2, map tokens to logits. Note that when we input something into a transformer, when we input something into any ML model in PyTorch, you need to make sure they're on the same device. So we're first going to move the tokens to the GPU, which is called CUDA for unimportant reasons. So yeah, we feed in the tokens. I'm going to use a method called runWithCache, which will also cache all intermediate activations. This is just pretty useful. We can print the shape of our logits. Yeah, generally good practice. Every time you ever make a tensor, print the shape and just keep the shape straight in your head. The shape is batch by position. Position kind of just means like sequence length. Here, shape is batch by position by d vocab. devocab just being the size of the vocabulary. So step 3 is convert the logits to a distribution, and so that means here we want to convert it to log probabilities using the log softmax method. dim equals -1 just means along the devocab dimension, the -1th dimension. We could also create probabilities, and yeah, so we can print the shapes of both. They're just going to be the same as the shapes of the logits, because yeah, log softmax doesn't change shapes. And we can look at what the model thinks the top token is for everything. That converts it to probability. Bonus step, what is the most likely next token at each position? I'm just going to write some tensor algebra. You really don't need to understand what I'm doing, but I'm going to take the argmax along the final dimension, and then this is going to get me a token position, and then I'm going to use model.tokenizer.decode on that, and I'm going to get rid of the batch dimension, and I'm going to use batch decode so it makes a list. So if we go and compare it, we've got like, I am an amazing autoregressive transformer, and after I, it's like, yeah, maybe let's print zip of this. Again, you really don't need to understand what I'm doing. This will let us see what it thinks is the most likely next token after each thing. So it thinks I goes to I am to A. I am an to a word beginning with a vowel. It's like pretty solid. I am an autoregressive, it thinks it's a full stop for some reason. And so now we can sample from the distribution. The thing I did here was just greedy sampling, take the biggest value. But we could just like add the token space I to the end and see what it does. Map distribution to a token. So here I'm just going to do like next token equals final thing in the logits.argmax, and that is going to give me a thing which is going to be space I, and then step 5, add this to the end of the input and rerun. And I don't know, there are more efficient ways to do this. Yeah, there are more efficient ways to do this in real models, but whatever, it doesn't matter conceptually. And so, yeah, let's make like next tokens equals torch.concatenate, write some random boilerplate, to like get PyTorch to be happy. This is really not interesting, you don't need to worry about this. And now we can get new logits is the reference model run on the next tokens, and we can print out what the new logit shape is. It's going to be the previous thing plus 1, and we can print out what the final argmax is, and oh yeah, I should import PyTorch. I definitely am going to need PyTorch, and I'm definitely going to need NumPy at some point, and I'm probably going to want the math function at some point as well. So what does this think the next token is? Yeah, now we can decode. Yeah, so the new input is new tokens as text. It's model.tokenizer.decode. Oh, we probably want to remove the batch dimension. Tokenizers are a pain, man. Then we print the shape of the new tokens, because you always print shapes. Yep, we appended space I to the end, and it thinks we should put space am. Great. So, high level, what is a transformer? Just to recap. Takes in language, predicts next token for each token in a causal way. We convert language to a sequence of integers with a tokenizer. we convert integers to vectors with a lookup table. Output is a vector of logits, one for each input token. We convert to a probability distribution with softmax and can then convert this to a token, e.g. taking the largest logit or sampling, or you can do loads of shit, not super important. We append this to the input and run again to generate more text. And that's part of what we mean when we say the model is autoregressive. Oh yeah, I think I used the jargon decoder earlier, a decoder only earlier. Basically means autoregressive. It's not super important. It's just some random old garbage from how people originally defined transformers back in the ancient days of yore of like 2017. God, AI moves so terrifyingly fast. It's awful. Meta level point. Transformers are sequence operation models. They take in a sequence, do processing in parallel at each position, and use attention to move information between positions. I'm just gonna emphasize shit like this a bunch because I think it's just really important to really carefully keep in your head. Okay, we're gonna move on to implementing a transformer. If you've skipped ahead because you weren't interested in the what is a transformer bit, you should pause the video and go read these key takeaways. What is a transformer? So here is a beautiful diagram I cribbed from the Mathematical Framework for Transformer Circuits paper. Credit to Chris Oler for being really good at graphic design. High-level architecture. This goes from bottom to top. I'm going to write top to bottom. So what do? Input tokens is integers. Embedding is a lookup table mapping tokens to vectors. They live in the residual stream. The residual stream is like the central object of a transformer. We have the sequence like x0, xi, xi plus 1, xi plus 2, etc. What's going on is that each layer of the model reads in the accumulated sum of all previous layers, and its output adds onto that. And this central object is called the residual stream. The way to read a diagram like this is that these are skip connections. This is really, really conceptually different from something like a standard network, where each layer's output is the previous layer's input, rather than the sum of all previous layers. My understanding is that most of the computation done by a transformer is not actually going via all of the layers. It's going via a head in layer 1, an MLP in layer 3, a head in layer 7, an MLP in layer 24, and then gets to the output. Go watch my transformer circuits walkthrough if you want more. Then we have a series of n layers transformer blocks. So a transformer block is a stack of an attention layer and an MLP layer. Confusing jargon, a block contains an attention layer and an MLP layer, but we say a transformer has k layers if it has k blocks, not k of 2 blocks, jargon, whatever. So if you understand a single block, you just understand the entire internals of a transformer. It's just the same thing repeated, because why would you do anything else? So first we have attention. This moves information from prior positions in the sequence to the current token. We do this for every token in parallel. This is a pretty important point. When I say current token, I don't mean the final token, because the way a transformer works is it's doing the same computation at every token position in parallel using the same parameters. The only difference is that we look backwards only, and this produces an attention pattern. For each destination token, a probability distribution over prior tokens, including weighting how much information to copy, a fundamental point, figuring out which source tokens to copy info from is a separate circuit from figuring out how to copy that information. So I just wrote a bunch of jargon. What do I mean by this? You should go watch my transformer circuits walkthrough if you want more. Yeah, let's move this to the top. So what's going on here? So the attention is the only bit of the transformer that moves information between positions, and it does this by, for each token in the sequence, looking at previous tokens. Previous because it's causal and predicts the next token, and we can't let it look to the future. This means that later tokens get more room to look back. We look backwards so we can predict the next token without cheating. Every bit of the transformer is doing the same computation at each position. Xi is like a big tensor that has a residual stream vector at every position. The two key things to understand with an attention thing is you look at each pair of tokens, destination tokens, which is the later one, and a source token, which is the earlier one. They can be the same token. What we do is, for every pair of tokens, we have a weight called the attention pattern, or like the attention pattern paid from that destination token to that source token, that chooses how much information we copy from that token to the current one. Two important details. The way we copy the information only depends on the learned parameters of the model. It doesn't depend on either the destination token or the source token. What information we copy does depend on the source token, but it depends on the residual stream. Like, if the source token has gotten a bunch of information from its context, this does not necessarily mean the info of what text token is at the source token's position. Like, if I feed in the string hello world exclamation mark, and the exclamation mark attends to the world token, it might be the case that the earlier head attended from world to hello, copied the information that was hello, and created a feature saying this is a programming thing, and then the exclamation mark copied the programming thing feature, but not the world thing. Generally, the intuition here is that the residual stream just contains a lot of contextual... It contains just information the model wants to move around. The residual stream is how the model moves information between positions, so like how the model remembers things, moves information between layers for composition, and can move between positions, including via other tokens. Go watch my transformer circuits walkthrough if you want more takes on how to think about attention. The final point is that the attention layer is made up of several heads. Each head acts independently and in parallel. So what I've actually described here is each head. What a head does is it learns its own attention pattern and own information about how to copy things from source to destination. Oh yeah, note that when I say copy, I mean apply a linear map. And yeah, so each head basically does the thing I described here. Let's just like reorder this section because I think that would make it conceptually clearer. The heads act independently and additively. We just add their outputs together and back to the stream. Maybe I'll just create a high-level thing about the residual stream. The sum of all previous outputs of layers of the model is the input to each new layer. Yeah, so going back to the diagram, I just talked a bunch about what attention is and how attention works. Then I need to talk about the MLPs. So MLP stands for multi-layered perceptron. It's basically a standard neural network. That is, it looks like linear map, normally going from small to big. Like normally the internal dimension is 4x the size of the residual stream. Then linear map from big to small, back to the residual stream size. And in the middle, there's an activation, normally a GELU. If you come across ReLUs, GELUs are basically the same, but they look like this. And kind of in the limit, they basically look like a ReLU, but they're kind of curvy and a bit more bowl-shaped and can go negative. I don't really get why GELUs work, but empirically they work better than ReLUs, so everyone uses them. Single hidden layer, linear map to GELU, activation, to linear map. You could use like a ReLU. Anthropic has this great paper where they use softmax, where they use a kind of funky thing called SOLU, which is a softmax-based thing. Exact activation, not super important. Middle dimension, normally, so we call it DMLP, and it's normally 4 times the size of D model. Oh yeah, each head has internal dimension of the head, and this is normally going to be D model divided by number of heads. Exactly why the ratios of are what they are isn't super important. It doesn't actually matter that much, and people basically cargo cult what GPT did. ML is weird. Lots of things just don't matter, especially with transformers. Intuition. Once attention has moved relevant information to a single position in the residual stream, MLPs can actually do computation, reasoning, look up information, etc. Currently, a big open problem in transformer mechanistic interpretability is what is going on inside MLPs. See Toy Model of Superposition paper for more on why this is hard. Yeah, in brief, transformers do more computation with their MLP neurons than they have neurons via compression, and it's a fucking nightmare. High-level intuition about machine learning. If you have a linear thing, and then a non-linear thing in the middle, and then a linear thing, this can do weird computation. It is the most powerful force in the universe, and can approximate arbitrary functions. And no man, it just works. Finally, we unembed. This means apply a linear map going from final residual stream to a vector of Logits. This is the output. So yeah, that's like the fundamental core of how a transformer works. So just briefly recap. Tokens, these are integers. This is a batch by position tensor of integers. Batch just means we're inputting several inputs at once, because this is useful for boring reasons. This is just how we train models. Then we embed it. We convert them to vectors. Then we apply an attention layer. The attention layer is made up of several heads that act independently in parallel. Each head has an attention pattern. It moves information from source positions to destination positions for every pair of tokens, early one source, late one destination. It then applies a linear map to the information at each source token and copies that information to the current token position, and each head acts independently, it's got its own parameters, and then it adds them all to the residual stream. The MLPs are a linear map that projects the residual stream to a bigger space, applies nonlinearity, yellow, and then projects back down to the smaller space, and just adds its output. You just do this a bunch of times. I don't know, I think GPT-3 has 96 layers. Transformers are weird, man. They get really big. And then you apply a linear map to convert it to Logits. And that's the core thing of how Transformer works. Just some bonus things, less conceptually important, but key technical details. So there are two things I did not explain in there that matter. The first is LayerNorm. So LayerNorm is kind of the equivalent of batch norm, for people who come across that is applied at the start of each layer. And it's just a simple normalization function applied at the start of each layer, MLP, attention, and unembed. So it converts each input vector independently in parallel for each batch by position residual stream vector to have mean 0 and variance 1, then applies an element-wise scale and translation. Okay, so what's going on with LayerNorm? So the maths for LayerNorm is you start with x0, and I'll change my variables because we use that for the residual stream. So y1, so y0 is the input, y1 is y minus its mean. An important note is that LayerNorm is actually a pretty conceptually neat thing if you look at things from the perspective of being vectors. So I'm going to rewrite everything as I say it in terms of linear algebra. It's not super important if you don't follow this, but I think it's worthwhile to try to understand it. We basically project y, so we're basically dotting y with this vector, the all ones vector, and divide by root n, so it's a unit vector. This gets a scalar. We then multiply that scalar by the all ones vector and divided by root n. And if you do the maths, this is just exactly equivalent to what we did here. And importantly, this means we're just removing one dimension. I'm pretty unconvinced this actually matters, to be clear. I think the mean part of LayerNorm just doesn't really matter, and you should probably use root mean square norm, which gets rid of the mean reduction, because, I don't know, this is morally equivalent to just setting the first coordinate of y0 to 0. It doesn't matter. Then we do y2, which is we divide by the norm of y1, or rather we divide by the standard deviation of y1, which is the norm over root n. This just forces the norm of y to be root n. This just makes it variance 1. Mental picture is, if you're in 3D or 2D, this is like taking the unit sphere or the unit circle, taking the direction for y, and then projecting it onto a circle with radius root n. In higher dimensions, you're just projecting onto some fixed hypersphere whose radius is root n. Again, you don't need to understand the linear algebra framing, but I think it's useful. Then we do y3 is y2 element-wise multiplied, I don't know if that's a standard symbol, by a vector w in r to the n. This is equivalent to y2 multiplied by the diagonal matrix whose elements are in w. This is important because this means that the second bit of LayerNorm is just basically applying a linear layer, and then y4 is y3 plus some bias vector. Note that this is wildly unprincipled because w is defined in terms of the kind of standard or canonical basis for the residual stream, just like the actual numbers you see in the residual stream as like represented in the computer. There's no intrinsic meaning to this, as I talk about in my transformer circuits walkthrough, and LayerNorm kind of tries to make that basis matter, and this is fucked. But turns out there's this cute trick you can do called folding in LayerNorm, where if you, let's write this at the bottom. So if you're folding LayerNorm, so you're going to feed it into another linear layer. So let's call this W, let's apply everything on the right. If you map y4 to y4 w2 plus b2 is another linear layer. This is equal to y2 times diagonal w plus b times w2 plus b2, and this is equal to y2 times the composition of dw and w2, which is just n by n matrix, or n by the output dimension of w, let's call that m, and then you add on the bias. And this lives in r to the m. And this means you can basically think of LayerNorm as kill one dimension, scale. Because LayerNorm is only ever followed by a linear layer in GPT-2, you can kind of just conceptually think of LayerNorm as literally just being what I'm talking about here. Cool maths tangent. LayerNorm because LayerNorm is only applied. Yeah. So scale and translate is just a linear map. LayerNorm is only applied immediately before another linear map. Linear compose linear equals linear. So we can just fold this into a single effective linear layer and ignore it. My library does this automatically. The fold ln equals true flag in from pre-trained does this for you. A common mistake I see is people just don't do this, and then they try to use the weights from a layer, ignoring the LayerNorm weights, and try to think about, say, how the output of layer 1 composes with the input of layer 2. And this is just, like, incorrect, because the input to the layer goes via the linear map of LayerNorm. Anyway, the final point is LayerNorm is super fucking annoying because the scale part is not linear. So you can't think about different bits of the input independently, and I hate it. And massive tangent on LayerNorm, you do not actually need to understand this, but like, it is useful to conceptually understand every bit of a transformer in order to get your head around it. The final thing is positional information. So this is totally fucked. Okay, so why does this matter? So the key problem is attention operates over all pairs of positions. This means it's symmetric with regards to position. The attention calculation from token 5 to token 1 and token 5 to token 2 are the same by default. This is dumb because nearby tokens are more relevant. Like, the way to figure out what token comes after my cursor is to look at more. A lot more than looking at dumb. So there's a lot of dumb hacks for this. We'll focus on learned absolute positional embeddings. This means we know a lookup table mapping the index of the position of each token to a residual stream vector and add this to the embed. And yeah, so if we just go to this diagram, what we do is we just add in a positional embedding. This is just another lookup table, and then we add it in here. There's a bunch of other ways you can do it. I hate all of them. I think learn positional embeddings are like the least cursed, but they all suck. And this is how it's done in the model. The library includes the code for rotary embeddings and short-former style embeddings. There's also sinusoidal embeddings. I hate positional embeddings. I'm not going to talk about this anymore. The final point is that we add rather than concatenate. This is because the residual stream is shared memory and likely under significant superposition. We compress more information in their or rather, the model. Generally, just like every layer adds to the residual stream. It would be kind of weird to have like a dedicated bit that's added. I don't feel like I've got a deeper argument than that, to be honest. Residual stream, shared memory, likely under significant superposition. We basically never concatenate inside a transformer unless doing weird shit like generating text efficiently. You don't need to worry about what that means, but you can go read the easy transformer code about caching if you want to understand it. I think it's reasonably cleanly implemented. Alright. End long conceptual description of how transformers work.